Go.
All right, so this is my presentation. The research I did is about antibacterial properties of select antioxidants. And my mentor is Dr. Luke Health. All right, so you live in a time when there are a lot of problems with antibiotics. Antibiotics have been used as treatments for bacterial infections over the course of many years, since penicillin was first discovered ever so long ago. But recently, we've been seeing a rise in the number of bacterial species that are resistant to antibiotics. So this graph on the screen shows, as you can read, a decline in new antibiotics being produced by pharmaceutical companies, and an increase in antibiotic resistance. And then the WHO, or the World Health Organization, has said that no major antibiotic has been produced for 30 years. And so because of this situation, scientists are trying to come up with new ways to treat bacterial infections. And something that I looked into was antioxidants. And these are chemicals that are naturally found in foods and in the body that are used to bind to chemicals called free radicals. Some examples are superoxide and hydroxyl radical. What these chemicals can do, they can bind to important cellular structures or molecules like proteins and DNA, and they can cause mutations or permanently damage them. And so other functions of antioxidants have yet to be discovered. I first was interested in researching antioxidants because of an article that I came across. And this article was a presentation done in 2014 by this research group before the American Chemical Society. And from what I understood, it wasn't a finished study, it wasn't a published study, it was just a presentation that was done on the effects of honey on bacteria. Some of the reasons that this group gave as to the antibacterial properties were antioxidants, osmotic pressure, the pH of honey, and the presence of other chemicals. So I decided to pursue the antibacterial properties of antioxidants. As I kept on researching, I found a few studies showing correlations between the antibacterial properties and antioxidant properties of different extracts from grapes and also tea. And they show a correlation. They show the correlation between those two properties. And so the important question that I was asking is it the antioxidants that is causing the antibacterial properties? Because correlation does not necessarily mean causation. And so what I did, I took a number of antioxidants, took 3 antioxidants as well as honey by good old food land, and I decided to test them against 5 different types of bacteria. One Staphylococcus aureus, methicillin-resistant Staphylococcus aureus, Lactobacillus acidophilus, Pseudomonas aeruginosa, and Escherichia coli. And so, citric acid, rutin hydrate, and azotic acid are the chemicals I chose because of their availability in foods, mainly citrus foods like oranges. And citric acid and azotic acid are both organic acids. Azotic acid is also known as vitamin C. And rutin hydrate is another type of chemical called a flavonoid, in addition to being antioxidant. So what I did is I followed what is called a Kirby-Bauer method. For these types of studies where you measure the antibacterial properties of certain chemicals, you have to follow a very specific protocol, which is the Kirby-Bauer protocol. That involves taking agar plates and swabbing them with bacteria and then adding the small paper discs to the plates, and then injecting the chemical onto those discs. After which you would incubate them, and you measure what is called the zone of clearing around those discs, or area, these little circles where there is no bacterial growth. And so that's a brief overview. And as a positive control, I've used 100 micrograms of penicillin, which is an antibiotic. To go into a little bit more detail, what I did, I took several colonies of each of these bacteria, and I made different solutions. Well, I made a solution. I combined the colonies with what's called phosphate buffered saline, or PBS. And then I would have to, I guess, standardize or try to make each solution of bacteria the same cloudiness or turbidity. And the way I did this is that I had what's called a work your hand card, which is a series of black and white lines. And also I'll use the McFarland standard, which is where you can see in the picture. It's a tube with a standard amount of chemical inside it to make it appear somewhat cloudy. And so I pulled a tube of the bacteria in the PBS, and I held it next to the McFarland standard, and I held the card behind it, and so I could gauge the cloudiness of the solution. And then I would either add some more bacteria, or I would add more PBS to try to get it about the same. I remember Dr. Scott walking in on me one day when I was doing this. He just kind of chuckled at the method. But it's what I had to do. And so after I standardized the cloudiness of the solution, I swapped the bacteria onto petri dishes of Mueller-Hinton agar. This is also the type of agar that you would use for these types of tests. So, and these are the results of it I got. I'm sorry, I forgot to mention that I also made solutions of each of these antioxidants, as well as a number of negative controls. And at the beginning of my study, my purpose was just to look at each individual chemical that I was testing and seeing how low a concentration I could make the chemical and still have some antibacterial property. So in hindsight, I should have tested each chemical at the same concentrations, but this would have been hard to do because of the solubility of each chemical. And I'll go into that a little bit more at the end. So these are the results I got. As you can see, the antibiotic control showed significantly more antibacterial activity, which is shown by the zone of clearing around the paper discs. And the control showed a lot higher antibacterial activity at a significantly lower amount of chemical added. You can see I use 0.1 milligrams of control as opposed to, for instance, 2 milligrams of ascorbic acid. And these results are more or less consistent through each bacteria tested, which I thought was pretty interesting. So we have E. coli, Pseudomonas aeruginosa, and then Staphylococcus aureus. And then we have MRSA and Lactobacillus acidophilus. So obviously, as we look through the results, you can see that the 6.5 milligrams of citric acid showed the highest amount of antibacterial activity, which is also the chemical that I tested at the highest concentration. And I should point out that rheumatoid hydrate didn't show any antibacterial activity, so that's because the solubility was low, and so I had to make solutions of lower concentration of the root and aggregate. And interesting enough, the honey also did not show any antibacterial property. Well, it didn't show any zones of clearing. We'll talk about that a little bit later. And so these are my conclusions. Is that, as I mentioned, the antibiotic showed a higher amount of antibacterial activity than the chemicals tested. And this showed even against methicillin-resistant Staphylococcus aureus, which is resistant to methicillin. So it is a different antibiotic, but the carbonicillin didn't have as much of an effect on that bacteria as compared to other bacteria. Another conclusion I made is that antioxidants have to be at extremely high concentrations they have to be at extremely high concentrations to be effective. Some of the studies that I read, these extracts of grapes, the researchers found that they were showing inhibition at around 1,000 parts per million. And if you do the math, the concentrations that I was testing the antioxidants in were 130,000 parts per million. So big difference. So 130 times greater, they're showing antibacterial properties.
Say that again.
So the antioxidants, they had 130 times greater the concentration as opposed to the extracts of these other studies.
Oh, okay, okay.
And both showed antibacterial properties.
Which suggests that it probably wasn't the antioxidants in those other extracts then?
I think so.
Okay.
And actually, it makes me wonder what is the reason behind the antibacterial properties of the solutions that I made? Is it because there's just so much stuff in the solution, or is it because of antioxidants? So that is definitely my question. And that's something that can be researched further. And so future studies can be done to test even more antioxidants, and also to test test extracts taken from food. Perhaps researchers can take extracts and find all the different chemicals that are in these extracts, and then test each individual chemical against the bacteria to find out which chemical specifically is causing the bacteria to die. And as I mentioned, I had some problem with the solubility, and to get around this, what future researchers could do, as Dr. Luca and I discussed, we could add a certain amount of chemical to a disc and let them dry, and then we could add even more solution to it and let it dry, so that the chemical is trapped within the disc, but the water is evaporating, or the solvent is evaporating, allowing for more solution to be added until you have until the amount of chemical is the same for each disc. I hope that makes sense. Okay, good. And so I would like to acknowledge first and foremost my researcher, Dr. Lukov, my research mentor, Dr. Lukov, for his support and his guidance in helping me with this. And I also had to go to Dr. Gold. I also went to Dr. Gold for his advice. And then also thank the biochemistry department for giving me this opportunity to do the research, and also Brigham Young University for their